center of research. I mean, Barry O'Sullivan is, for instance, one of my co-PIs there. So there is another connection there. And those who know me already from last year, they know that I do actually formal methods. I do system building, complex systems that have, you know, to work well together, different parts of it that work well together, and combined with formal methods that basically means models and properties, right? So the proper title is actually Digital Twins and Active Automata Learning, and I'm going to try to explain to you what they have to do with each other. Okay, but the real, let's say, mantra is the unbearable lightness of models, how cool it is to have models, okay? Digital twins are models, okay? So a little bit about the context. I'm just using a couple of slides that we used in the 2-year SFI review of Confirm, okay? Where I am the co-director of the Cyber Physical Manufacturing System Hub. So this comes from there. We had to explain that we are, you know, doing activity. Now it is Science Week, okay? So we are doing activity that is also understandable and acceptable, so to say, to younger students or to students that are in different areas of expertise. So if you look at here, for instance, at the top, there were transition year workshops for students in the schools where we showcased actually what we are doing in the hub. This is Alex Shivek, is my PhD student. We had students over the summer from France that came with an Erasmus program, and they also worked with us to do models, okay, for robots. And we also had a component, to say, of modeling, especially this kind of modeling in a summer school at the beginning of the year in Stellenbosch. So there is a lot of outreach around that, right? And this is connected actually with Hub 2, which is the cyber physical systems. In the big picture, this is the big picture slide, so to say, of Confirm. You see that there are many activities going around in different hubs, in different areas of fundamental research about self-aware manufacturing, test beds, virtual industrialization, and so on. And what we are doing actually is the cyber physical in the cyber physical manufacturing system, CPMN, MS. If you read these headlines, there is a lot of space for ML and AI in there, okay? So if you're doing security and analytics for these systems, or heterogeneous data integration, or network control, or dependable networking, or whatever, so it is all connected, right? So in the in that review, what we showed is actually the vision for the future. We would like to have a reprogrammable factory that starts with an idea, with a business model, and with a business logic, and basically is able, by means of you know, various reification, concretization steps, to come down to a physical test and deployment in the digital manufacturing on the floor, right? And you see that there is a big thing, a big white box, so to say, in the middle, which is the one that basically couples and decouples those two parts, right? So in reality, you cannot go directly and experiment on the floor. What you need is some way of actually reflecting what is happening on the floor in models by means of digital twins, okay? So that you have a hosting and emulation environment that basically allows you to describe what is going to happen and predict what can happen if you change something, right? Or if you monitor something, etc. So the digital twin is pretty central there, okay? So what did we present from my research, so to say, in that context? Well, something that created quite an aha effect, okay? There were two aha effects. One was basically, okay, showing this tiny little video. That's the same Alex that you saw before. What he's doing, he's basically controlling the robot from a web application. And that was a big aha, okay? Right now, a lot of manufacturing systems, they are not web enabled, they don't have HTTP, they don't have REST services or something like that. And so you need to be really there in order to program what happens. So the ability actually of lifting the controller through the web was, of course, great. And we showed them also another thing, so this tiny little model. I told you that I like automata, okay? So this is a tiny little digital twin of what this controller for the robot can do. And the cool thing of that is that it was, how could I say, generated, not created, okay? It was not handmade, but it was automatically discovered by means of active automata learning. And that's the connection between a digital twin and the AAL, okay? So it's a MIDI machine in particular. It was created with a LearnLib, but you could have also done some parts with Alex, which is another tool, which is much nicer to use, okay? And so we are going to talk a little bit about that. So question, but Tiziana, so you always do model-driven development. Why do you have this model? Don't you have a model for the programming, right? And I says, yes, and not just one model, actually a lot of models, because in the digital thread, which is part of the digital twin working, we are actually using extreme model-driven development with a lot of less programming, low-code environments, and more models or so. So if you look actually at the GUI, so to say, of this web app controller, I think that I have even a pointer here, okay? If you look at this one, we didn't program that GUI. No, we just composed it from a library of GUI elements in a design environment that is a tool with a graphical composition of models. And once you have basically dragged and dropped those components and you have named them properly, so this robot can do a couple of things. It can reset itself. It can go to a certain position. It can go to a 0 position, go to a test position, etc., etc. So it has a six functionalities, okay? Once you have this, basically from the GUI model, you can already create the first part of the app model, which is basically a process model, a behavior description model for what is going to happen, right? So, you see that there is this symbol for this page, and then you have here 6 options, which are the next actions. And guess what? You have here 6 branches coming out of that state, if you want to call it a state, okay, labeled exactly with the label that you find on these buttons in reality, right? And so basically, if you drag this here, it has already those 6 legs out, okay, correctly labeled, and you know that you have to define something else that is happening when you actually do that, ask for that option, right? There are some further pages, there are also some real models, okay? Just imagine as if it was calling a procedure, right? So you can have basically models that are expressing the use case workflow, okay, for that specific case. So it's a process model again, right? And if you just want to look at it in a different way, it's also a finite state machine in a certain sense, control flow graph and data flow graph, right? So the control flow, of course, are these full arrows. The dotted arrows here, they have to do with the data. What kind of data do we have? Well, we have a complex data, which is basically a set of coordinates, actually 2 sets of coordinates, because it is the starting point and the end point in a 3D space of this robot arm that is moving from 2, okay? So this is exactly taken from a class model, from an entity relationship diagram. It's your data model. And once you have those, basically you don't need to implement much, because the UR3, this robot, comes with a domain-specific language, which is an API, which is basically a collection of services. So you can have a service-oriented computing way of doing things, right? So if you look at this, well, that's a lot of models. It's a lot of automata. Why do you need this other model? Well, this is the prescriptive set of models. We use them in order to generate the code that is implementing the controller, but maybe we have a mistake in the compiler, okay? Or maybe we forgot something or whatever. So what does the system really do? Can we establish that independently of this model or of the code that we could have written per hand, okay, as a native code? And the answer is yes, okay? So this model is actually not generated from those models, but it is generated by basically testing, okay, systematic testing, by interacting with the system as if it was a black box, forgetting how it is programmed, okay? And then we can basically have an independent, let's say, creation or establishment of what is the possible behavior of this system. And if you look at this in a little bit more detail, you see that it is one machine, okay? It's a finite state machine with a starting state, which is this one, with a lot of loops, okay? Every transition is labeled with all the possible, let's say, operations that you can have, go to a certain robot position, go to certain coordinates, cancel the coordinates, etc., okay? Some of them are labeled as successful. Some of them have data, okay? So you start to see, okay, wait a second, this is probably a milli machine. It is a milli machine that considers data, okay? So it is not really a very simple model to learn, okay? And we basically, the rest is going to explain you how to create this kind of models, okay? So it is learning-based testing in the category of machine learning called active automata learning. So it is actually discovering behaviors in a systematic way, okay? So where does it come from? It comes from actually over 20 years ago when we worked with Siemens in a CTI project, Computer Telephony Integrated Systems, where they had testing problems. They had a lot of PCs. They were starting actually to have significant PCs that were integrating with phones. They had their switch and with a lot of phones and the ISDN network, which is not HTTP. It's a completely different kind of protocols. And they had basically a way of integrating them, which was the LAN. Okay, and they had a huge problem because there were a lot of applications that were actually doing telephony on the PC. And so they had to test that any change in these applications, 300 of them, was actually behaving properly in the context of a very complex switch, okay? So what we did, we basically started to generate models of the tests and started to apply those tests in a systematic way, right? That was fine for a couple of years until basically the internet wave came onto them, and they started to have much more complex networks with redundant clusters, for instance. So instead of having just, you know, one switch and a couple of phones, they started to have a constellation of switches, in this case, for instance, 4 of them that are working in a redundant way, and they had to start actually discovering what is happening in the handovers and in the communication inside this system. So same approach, HTTP on the PC side, rational robot using Selenium, still technology of today, and then this coordinator that is actually a little bit the brain, okay, of what is happening. And we basically started to experiment with tests in that context. So if you want to have a sort of a 2001 level simulation, okay, of the system, well, what happens? Well, you, in order to set up a test case, you switch on and reset, so to say, the test coordinator, choose your test case, then you prepare all the machinery, okay, you have to set up and start the application on the PC, then you have to start all the observers, which are basically the WHOSIM and the Hypermon and so on. These are basically the probes that you have at connection points in order to find out what kind of information is going around. You remember from yesterday, Katie, data fusion, that's it, across protocols, okay, with real hardware. Then you set up actually all these observers, et cetera, in a known state. And the application, you prepare it, okay, and then you just start making a call. So assume that you are actually starting to make a call that arrives at this switch, but it is handed over to another switch and it is anyway replicated on a different switch because of redundancy. Then what you have to do is to basically see that if you are sending an off-hook information, not, you know, message, so to say, to this destination switch, actually what is happening on the display locally at the phone and on the PC is exactly the same, right? This is your test case. At this point you look, okay, there is a machine that looks and finds out whether it is the same. You take your verdict, passed or fail, okay, and then basically hang up again, and then you basically return the entire system in a known state, so that you basically go down again to 0, and then you start your next test case again, okay? So if you want to do it by hand, that takes forever, okay? So we started actually to learn models. It was a major test suite optimization, so a huge coverage difference. It was 100%, so to say, instead of just a few percentage, okay? Much more compact test cases, huge advantage, okay? We were, however, doing it in a passive way. So just, you know, these are the cases that are happening, let's hope that they are all of them. There are a lot of configuration cases that are very rare. You remember from Nick's conversation yesterday, dealing with test cases that are rare, it's very tricky, okay? So we said, okay, so if we cannot wait that things happen, maybe 1/1,000,000th of a time or 1/1,000,000,000th of a time, we have to find a more clever way of doing this and basically steering the conversation ourselves. That's the active automata learning technique, okay? So we have to simplify life, abstract. For instance, if you have a very complex message like this one, it is going to just become, okay, there is an event on device A1, and it is an on-hook, you know, event on the switch, instead of all this stuff, which is actually the CSTA protocol, okay? And then basically we try to learn automata that have this language on the right, okay? The automata that we looked at were typically I/O automata with some modifications. They are inputs. Inputs must always be enabled. The outputs are system controlled. They are modal transition systems because we need to have loose specifications, like saying, okay, eventually I can do something, always or never, okay? And we have very complex annotations because there is all this information, so to say, that is going around on the messages. So we have labels and information both on the states and on the actions. So these are basically KTS, Kripke transition systems, okay? So we started with those. Meanwhile, we have mini machines, Moore machines, register automata, register mini machines, visibly push down automata if you have actually procedures and so on, and more, okay? So this is 20 years of research, right? How does this work? Well, it is extrapolation. You build hypotheses of how this automaton, this model looks like, and you build hypotheses beyond known facts, okay? Then you check them, and you try to stay with regular languages. So the extrapolation universe is still finite state automata, extended finite state automata, because sometimes you have data, okay? And the moderation is actually a clever way of choosing what to do next, okay? So it is targeted interaction, okay? So, you know, from computer science, things have to be correct and complete, okay? Or at least correct and or complete. Bad news, it's neither correct nor complete, okay? So is it useless? Well, a lot of things that are neither correct nor complete, they are extremely helpful, like type theory, for instance, okay? What I can tell you in good news is actually that all the information that we have is optimally reflected in the models. And optimally means consistently, there are no contradiction, deterministic automata, okay? And minimally, this is the smallest automaton that is explaining exactly all the observations that we had. So instead of looking it from the system, did I discover the entire behavior of the system, et cetera, et cetera? Well, there are internal states and you may never be able to observe them, never be able to control them. Anybody that has done hardware design and hardware verification knows that there is the problem of propagation of differences to the outputs by acting on the inputs, because you have a black box. We are having a black box. So we are learning actually the behavior at the interface. That's why it was I/O automata, okay, of that black box. But if we look at from the point of information, so to say, that you are able to gather from interacting with the automaton, okay, all that information is optimally reflected and used, okay? So if you add information because you are able to access something else or something like that, you can continue from there, right? So it is optimal in this sense. How does it work? Okay, so we are going to go a little bit slow on this one, and then I'm going to go much faster, so to say, on the third part, which is the part, so to say, that has all the variants, okay? So let's assume that we have an unknown system, okay? And let's take the very first algorithm that was proposed, which is this L-star algorithm by Dana Angluin, 1978. I think that you were not yet born, okay, at that time. So she thought about that. It's a lady, Dana Angluin. And she just thought, okay, so how can I characterize an unknown system by making experiments from outside? And she was thinking actually in the context of a sort of a, mildly supervised learning, in the sense that she expected a teacher to be there who knows the answer, okay? So she devised a data structure for the discovery, which is called the observation table. which is basically, let's say, a complicated but very useful way of describing the automaton, okay? So here in the first part, we are going to have the lower hypothesis automaton. We are building an automaton, okay, in this part. It's growing, the observation table is built up and grows, okay? So we always have a current hypothesis, which is, okay, let's imagine that the system looks like this, okay? How do we call a state? Well, we don't have the names of the state. So we are going to call the state by means of the reaching words. So this is the state, assuming that you have an alphabet AB, okay? This is the state that I can reach by doing ABA. That's the name of the state, right? And yeah, and if I do AAB, I may land in the same state or in a different state. So we are going to have an encoding here of the states that basically tells us same encoding for the same state, different encoding for the different states, right? And then we have here the discovery of the transition. So when I'm there, what can I do next? Well, you can basically, try from each of these states the next action. So you have here just, the next transitions. And then we have to, we discover again where we land after these transitions. And we see basically whether we are discovering new states or not, okay? So we have here, with the comparison of this part of the table and that part of the table, we have the possibility of looking whether we are closed. So we have found all the behaviors that we could discover and whether they are consistent, okay? So let's try it on an example. Simple example, we have indeed a system that can do A and B. We are trying to discover a Moore machine, so there is no data, there is no output, it's very simple, just, the states, okay? And we encode as 1, the observation, this action is possible, and 0, this action is not possible. Like for instance, in our example of the digital twin, you can of course enter the coordinates, where you want to go, the robot to go, but you cannot do it on the start page. On the start page, you can only choose that you want on a different page, different state, enter those coordinates, right? So it is an action that is possible, but it is not available in that state, right? And so this is just, do we have, knowing the actions, okay, you know the alphabet, is it possible or not possible in that state? Okay, that's very simple. So we start with an unknown system and we know that we have the system, so there will be at least one state, I mean, a stateless completely system that doesn't exist in our state-based thinking, okay? So if we are at the very beginning and we are not doing anything, already we assume that there is going to be at least a state, okay? So we call this state 1, right? Then we start actually exploring systematically, right? Let's try to make an A. And let's say, okay, yes, you can do an A. So we just enter a 1. And you can try to make a B, like the coordinates, right? That I was mentioning, enter coordinates. No, you cannot enter coordinates. So it is a 0. Okay, now let's look at this. This is a not closed situation. Why? Well, I just assumed that I have one state that we call the state called 1, okay? But now I'm finding out that there is a different response of the system that I didn't consider before that distinguishes actually the answers. So this is a non-closed system. What do I have to say? Well, there are probably 2 states, okay? So what I can do is actually, to take this observation, put it up there, because I discovered that with a B, I land in a different state, okay? These are called membership queries, okay? It is basically a membership that this string is part of the language, okay? It was a regular language discovery, so to say. So it's, is this string, is this word a member of the language recognized by this automaton, okay? It basically checks the system reaction to input sequences, right? For what concerns us, that's the behavior. So now we have found out that B sends up to a different state. What do we do? Well, it's a different state. We do exactly the same game. We just add an A, try to do an A in that state, and try to do a B in that state, right? So now we have BA, and we have BB, and we find out that actually, okay, the system answers and says, no, you cannot do an A and you cannot do a B if you are in this after 1B, okay? So this is now closed and consistent. So we are still landing, let's say, in the 0, 1, let's say, states, okay? There is no new state. And so we could be finished, right? And the automaton would now look like this, because you have this state where you do A's. If you do A's, you land here. As soon as you do a B, after that, whether you do A or B's, basically you are in a non-accepting state. You also see, okay, so this one is an accepting state. That's the one state. This is a non-accepting state. It is the 0 state, right? So the encoding is correct. And if you want to give names to those states, you could call it, this is a state called 1, and this is the state called 0, okay, in this encoding. Now, are we done? Well, now we bring in the teacher, okay? We can basically go to some oracle that has the full knowledge of the system, and we can basically ask, tell me, is this the right model? And there is this oracle that says, nope, you are missing behavior. For instance, the system can do AB. And you see, I mean, there is no sequence AB yet, right? So in theory, you can have an oracle. In practice, if you had an oracle that knows the model, okay, you would not need to do all this work, right? We are doing this work because we don't have an oracle, because we have to discover, you know, by heavy work, so to say, what this system is able to do, right? So in reality, what you're going to use is some other independent knowledge. For instance, you know properties, and you have a model checker that is able to model check, you know, or you have another way like a compliance testing, comparison with a reference implementation, or whatever kind of other source of information that people in reality have, right? When they are dealing with protocol design, for instance, there is always a reference implementation that basically serves as the oracle, right? So you have means to come up with counterexamples. Okay, you are not sure that you're going to find all the counterexamples. So the incompleteness, for instance, comes from, this is one of the sources of incompleteness, right? That we mentioned before, right? So now assume that this oracle tells you, okay, you can do AB. What do? Well, we know now that this is a feasible sequence, right? So it goes up there. And if it is feasible to do AB, in particular, it must be feasible to do A, because you cannot reach a state that is feasible by going through states that are not feasible, right? So both A and AB enter, and because they are feasible, you have a 1, okay? And now what do? You do the completion game. You just take an A and add an A and a B, okay? AB is already here, and we already have the answer. We have to explore AA, right? These explorations are called, so these question of counterexamples are called equivalence queries, and they basically are checks for equivalence with a target system, assuming that you have a description, and produce a distinguishing test, which is actually what you are using. The trace, so to say, the run through the system described by the test is exactly what you are adding there, right? Okay, so now we complete those actions. So AB is already there. We don't have to do anything. We do AA, and let's assume that it is a 0. And then you have to complete also AB. So with ABA and ABB, and assume that these are the answers, so to say, what the system can do. So we have this situation. Okay, are we happy? Well, the system is closed, but, okay, let's start looking at contexts, okay? So we now have a state called 1, where you can either do nothing or do an A and you stay in that state, okay? Let's now consider, okay, what happens if you do an A after having done an A, okay? So those two cases. Well, this starting state, the underlined, so to say, 0, so nothing and an A, so to say, leave you in the big state, okay? But if after the first A you do another A, you land in a different, you land in a different state. So this A here, which is the successor to another A, and this A here, which is a successor to nothing, okay, distinguish the behavior in the future. So you have distinguishing futures. We split according to distinguishing futures, okay? So the rho epsilon is having the same, let's say, outcome as the rho of A, but the rho of epsilon followed by A has a different outcome than the rho of A followed by A. So A is a distinguishing future. We collect the distinguishing futures up here as columns. So we add an A as a distinguishing future, and we basically rerun, let's say, the experiments again, okay? And now, okay, we find out that it is closed and consistent. We wanted to have a small example, okay? And therefore, we basically create the automaton that is corresponding to this transition system. And this is the automaton, okay? So now we have an initial state. With an A, you go to another accepting state, which is this one, okay? With a second A, you go to a non-accepting state, which is this one, okay? And if you look actually at this encoding, okay, we know at this point that we are finished, okay? This is now the state called 1, 1, it is that one. We discovered even the encoding, right? This one is the one that you reach with the first A, which is this 1, 0, so we call it 1, 0. And the third is the state 0, 0, which is the one that you reach from the second A or from AB, etc., that we have basically discovered. They are behaving this way, right? So if you just look at this, basically we had a first hypothesis, which was, okay, we have a system, it has only one state and it accepts everything, sigma star, okay? We extracted by observation the part that was non-accepting, okay, in H2, which is hypothesis 2, and then we have the final system, which is hypothesis 3, which is basically this moderated regular extrapolation, where we basically separate only when we have evidence that it is a different state. Okay, so there are a couple of assumptions on the system. The set of operations that can be invoked has to be known a priori, for instance, from a public API. This is for the normal, let's say, Angluin. In reality, we can also then extend the alphabet on the go. Meanwhile, the reaction of a system to a membership query to a test basically must be observable. What you cannot see, you cannot distinguish, okay? So you're not discovering internal states, you're just discovering the internal states of the system that have an effect at its external behavior, okay? So you are actually creating a congruence, right? You are discovering the minimum automaton that is congruent with the set of observed behaviors. It's a congruence. You could substitute the automaton for the system and you would not observe any difference. That's why it is a fantastic digital twin generator. That's exactly what you want to do, okay? You have done a twin for this particular individual. If you had another machine that has maybe a mistake and it is not able to go to or to do something, okay, you would discover that difference because the system would respond in a different way, right? So it is an individual digital twin. You can have it at the type level, class of systems, so to say, all these printers or all these robots or so, or you can have it at the individual level. This one has a mistake and we can observe and we can discover it if we are just running the learning on that one. The system is deterministic. I mean, a lot of systems that exist in reality, they love to be deterministic. So it is a reasonable, let's say, assumption that you have, and you need to have a way of resetting the system when it is required. So basically, every test that you run, every membership query has to be independent of the previous one. So you're not running one test case starting in the end state of the previous test case, right? Which is exactly what we saw in the case of the Siemens complicated setting, right? So this is a summary of Angluin's algorithm. First idea, active testing with membership querying. That basically gives you a nice equivalence relation, okay? The second idea, you try to enforce consistency with the largest congruent, which is basically the Nerode relation, which basically distinguishes according to the futures, okay? So if I land with in different ways, so to say, to a state that has the same continuations, from there I have the same behavior, that's the same state, okay? And then there is the idea of actually this equivalence theory, equivalence query, so to say, which is a nice idea. It is practically not implementable, but we have seen that you have alternative ways of, let's say, simulating the equivalence queries, right? So I'm going to show you a couple of slides that a student generated in order to explain to other students, okay? So while the algorithm is running, he generated actually all the steps as for the intermediate automaton, okay? So you can see actually how it works inside, right? So on the left side, you have the current hypothesis, okay? And on the right side, you have the next step, okay? So you have a state, you have a system that basically only has one state. That's the big primordial state and soup, so to say, that we started with. So now we decide that this is an incomplete state and we have to explore it. Okay, so the alphabet is 0, 1. Okay, it's a different system. Okay, so we explore it. So we try actually, okay, we are there, we are in 0. We try to do a 0. Okay, we try to do a 1, and we get actually these answers. So this is now a completed state. Now we move it to the left and we go to the next step, okay? Okay, so now we go and continue. Okay, this is a completed state. We have done everything that we could do for S0, but S1 now is a new state. We have to explore that one. So we explore it and put it there. Then we find out that we have to explore S2, we put it there. Now we find out that we could simplify. Why? Because both S1 and S2 have exactly the same continuation. Well, we just said that in that case, they are the same state. So we just do it like that. We call them, okay, S1, okay? And we have an S0 to S1 relationship that in both cases actually sends us to the same state, okay? So you see that meanwhile, you can compactify your search. So it's not a tree. You're really generating at least a decision diagram, and actually it becomes an automaton. Then you continue your exploration, until you find out that this subtree is isomorphic to that subtree. So you can actually merge that way. Okay, so if we can go do this once and then do the same things another time, this is again one of the extrapolations. We assume that you can do it an infinite number of times, so you basically add the loop. And we are basically eliminating an entire subtree, right? So we start then to explore again, and we explore more, you can collapse more, okay? And you end up with this information. Are they equivalent? Are you finished? Maybe yes, maybe no. Okay, in this case, there is a counterexample, okay, which is the shortest prefix that actually delivers you a splitter, okay? So assume that the counterexample is this one, and basically the prefix is 110, let's call it 2, and the suffix is 10, let's call it the new letter. We just add a new symbol. We are doing numbers, and so let's call it, okay, we call 110 as 2, okay, the sequence. So you now think in terms of sequences because they are recurring, okay? And so now automatically, okay, this is auto-generated, you see now actually what happens. You are now exploring with an extended alphabet because we added the 2s and the 0s. You see that you are exploring, and then at some point you collapse, and then you explore a little bit more, and then you collapse, etc., etc. So it is 90 slides, okay? So we can just let it run. When I'm going to give you the slides, you're going to have the version with all these slides and the version without all these slides, so you don't have to sit there forever and you know, go through all this space. And you see that on the left, you're accumulating more and more from the tree-oriented exhaustive expansion to the collapsed information. You are becoming actually more and more an automaton. And so this is the final automaton. And this is basically, okay, the same kind of automaton that we had at the very beginning, right? Okay, so this is the Nerode theorem. Hypothesis automata have at most as many states as the system to be learned. You're not inventing states. And the hypothesis automata have at most as many states as the smallest deterministic system equivalent to it. And this is this optimality criterion that I told you before, okay? So from here, we stop going slow. Okay, this was the understanding part. Now we have understood how the situation was in 1978. We are a little bit later than that. So this is a lot of work and very slow, okay? So in order to make it useful, you have to be computationally much more efficient. You have to accommodate incremental learning. You get more information about systems while you go, because either they are changing, there are more alphabets, or because the organization of the system is changing, you know, self-healing, etc., etc. You have to instrument it properly in order to deal with data, and you need to become much more efficient. And that's why we created at a certain point an entire platform, which is called LearnLib. Just Google LearnLib and you're going to have the link where you have a gazillion of algorithms and pre-pairing and post-pairing and then analyzers, et cetera, for systems so that you can minimize the requirements on the system the way you want, maximize the outcome and the efficiency, and you can deal with a lot of variants of systems, models, algorithmic footprints. Do you want to have something small? You want to have something fast, et cetera, et cetera. So there is an entire platform for that, okay? So a lot of the optimization has to do with the analysis of the counterexamples. Okay, so what is the structure of counterexamples? For instance, you add all the prefixes as we saw, and then there is one essential suffix or so. You can work actually with that. Okay, just by basically distinguishing according to the essential suffix, and then having different words actually that go to that place. Okay. So Rives and Shapir, for instance, decided, okay, let's analyze the counterexample separately, not in the table, and then we just add only one essential suffix, which is a witness, okay, as the column label to the table. That was clever. So you have a guaranteed consistency and you improve, of course, the worst case complexity, but the hypothesis automata are no longer guaranteed to be minimal, right? So after a number of changes in 2000, I think it was 12 to 13, we came up with this TTT algorithm, which is space optimal and supports actually incremental learning, lifelong learning, okay, which is basically described in one of the two papers that I'm going to propose to you as literature club, let's say, exercise to do, okay? So it is a redundancy-free approach to active automata learning, okay? So if you have a couple of plots, for instance, standard system, which was the plain old telephone service. Okay, so how to phone with a service, with a phone when they were the old phones, you know, the white where you can only dial and answer and talk. Okay. And we compare actually the number of symbols and the number of tests basically that you need, okay, different symbols in three different algorithms. The Kearns-Vazirani, which use discrimination T's, so it is a DT table instead of the observation table. The observation pack algorithms that uses the DT plus this idea of Rives-Shapir, so to say, to do a separated counterexample analysis, and then the TTT, which is the one that optimizes the discriminators. And you see that the difference can be really orders of magnitude. And these are not Angluin. These are already optimized algorithms that came up later, right? So you have an almost constant behavior from the TTT algorithms, and the others, basically, they give up pretty early, right? We are doing here Boolean discovery, right? Just imagine in a real system with the software system of today or whatever, how many states you have if you have to encode them in a Boolean way, right? So the TTT algorithm is interesting, and it is called TTT because it adds actually three different optimization. A spanning tree, first tree, which defines the unique access sequences, okay? A discrimination tree for the distinguishing states, and a discriminator tree to store the suffix closed set of discriminators, okay? It is an extremely compact representation. It is the three trees, and therefore TTT, okay? And it strips basically away all the information down to the essentials for learning. So it's, in a certain sense, it is optimal, and it is, since its invention, so to say, the winner of all the competitions in this field, right? So that's the paper. So if you look at the queries, same story, okay? Because we are optimizing the symbols, we are optimizing the queries, okay? Again, TTT is the winner. There is a, okay, but this was a structured system. What if you do randomly generated system? Same thing, okay? And even here it is much better than the concurrency, so to say. So this is nice and good, but it is a lot of work. Can you automate more? Can you just, you know, make it easier to use? Well, this Alex and another Alex invented, let's say, a front end called Alex, okay, no puns, okay, for automata learning experienced, which is basically a system that simplifies largely the learning web applications and web services, okay? It doesn't require you to knowledge programming. It doesn't require knowing much about LearnLib, Selenium, etc., etc. It is open source, so if you want to play with it, go up there and use it. And in principle, it is able to deliver this kind of models, okay, for web applications. So the setting is exactly the same. Again, you have, you know, the learner, You are actually interrogating the system by means of tests, which are these membership queries, and you have somebody who is able to tell you whether you're done by means of equivalence theory. So it's queries. So it is exactly the same situation, and it delivers to you the model. Okay. For instance, I mean, if you just think in terms of an authentication system, it's important that you're not able to bypass, let's say, the authentication and to enter, you know, wrong credentials and get access or something like that. So it is very nice, actually, in order to find hidden states, right? So what is the difference? If you are working with a LearnLib, you actually need to be able to implement an application, implement a test, work with a LearnLib, etc. If you do it actually with Alex, well, the developer develops the web application, and then the quality control person configures, let's say, the learning through Alex, which is this web interface that foots internally on the LearnLib, and then you're happy and go, okay? It is just running by itself. Okay. So if you just look at how to learn, for instance, a web and REST interface of a simple web service, which is just a web service that manages a to-do list, okay, for you. This is the web service. What you do, basically, you have just to enable or define the symbols, okay, and their local answer. If you do it with web actions, you typically use on Selenium, which people are using also for model-driven testing, right? For the REST actions, you basically work with HTTP, send requests and analyze responses, plus there are typically a couple of general actions on top of that, okay, with variables, counters, etc. Okay. There are some things that can go wrong, so that's actually what the discovery mechanism is going to find out in your model, okay? And then there are two videos that I'm not showing now, but I can give you, okay, in separately, that are actually showing how to work with the system, okay? So basically, to set up the Alex, and then how the learn experiment execution really works, okay? So in order to validate the usability, we did a comparative study with 140 students. These are students of Web Technology 2 in Dortmund, okay? And they had to do quality assurance for this web application in 2 different years, okay? So in 1 year, they were, in 2014, they were doing it by means of their programming knowledges. So they had to do you know, design test cases and you know, assert whether the implementations were okay or not, okay? And not many students, so to say, were able to come up with a convincing answer, basically because it's a lot of work and the programming knowledges were not sufficient, okay? This is actually the following year where they were offered also the opportunity to use Alex. And you see that actually over 2/3 of the students, 3/4 almost of the students, were able to create a very convincing quality assurance report for these, actually for 26 implementations of the same to-do list manager app. Okay, and there is a paper on this one. Okay, so this is for the ease, okay. But then, okay, the future was also not looking really, really good because, okay, you saw already, I mean, there is always data somewhere. There are systems with procedures and so on. So how do you do that? Well, here is basically the second paper that I'm going to provide to you, which is published in the Journal of Machine Learning. So this is effectively machine learning. And it was about dealing with data. And it was the seminal paper about learning register automata from languages and going from languages to program structures, right? So you want to learn realistic models that look like the software, okay? Or the software models that you are used to deal with when you are doing, for instance, model-driven development in the traditional way, when you are, you know, using finite state automata for these kind of things, right? So the way it works is, again, the same, right? You have a mapper basically from L star, which is your abstract language, to the system under learning, okay? Which is including, like in data flow analysis, as usual, you have basically an abstraction Okay, and the concretization function. So what I showed at the very beginning with a very complex message that was becoming something much simpler at the level of the symbol that you are dealing with in the model. This is exactly the same game that we are doing, only that we are now explicitly having an abstraction and a concretization functions, okay? So if you have, for instance, a stack of capacity 3, okay, you will have a finite capacity, okay, and then you basically have a description, so to say, of what means to do a push, what means to do a pop in a certain programming language. So this is actually the system that you're trying to learn, right? Okay, so what comes out is that you can have different lenses, okay, on what you see and what you don't see in the system. So if you just stay in the good old world that we had so far, you just see the operations. So you start in L0, you can do a push, you come to L1. If you do a pop, you come back to L0. If you do a second push, you go to L2, etc., etc. And then there are going to be, you know, accepting states, which is up to filling the stack, which has a capacity 3. And then there are going to be non-accepting states when you try either to push too much or to pop too much, right? So this is the setting that you have, okay? This is the kind of messages that go, okay, so you see just the push and pop as abstract operations, and you basically see, okay, does it belong to the language or does it not? And then the concretization is that, okay, I'm pushing this symbol 1 and I'm popping the symbol 1. And then you can basically do it, be able to do it, not be able to do it, not have these this operation at all, or you can basically see the symbol that return the symbol that has been pushed, right? So if you look at it a bit more in a detailed way, you would like to know whether the operation is okay, okay? Okay, you push, the operation is okay. When you pop, what do you pop? Well, I push the 1, and so I'm popping that one, okay? And then some things are not okay, and this is null, so you have actually already more information, right? You can do it just by, you know, pushing the first, or pushing a 1, pushing a different symbol, etc., etc. So you can, you know, push the 1, push a 2, and then see what you are retrieving. So are you retrieving really the data that was pushed at that point, or are you retrieving something else, right? So you see that we are adding more information, and the labels become more complex, both in the input and in the output. You are seeing more things, okay? You could also start saying, okay, we want to have an abstraction. I'm not interested in what kind of number it is, just whether it is an even or an odd number. So you can include abstraction, okay? And so push, push, pop is basically, okay, an odd, push, push, push prime, pop is an even, okay? So, and you can basically start to compare what are the concrete sequences, okay, and the abstract sequences. And if you see that actually, okay, so what you are expecting actually is that this sequence is possible, and what you are receiving after you have done through the model, okay, so after you have done the abstraction and the concretization again is a different answer, well, that basically means that somewhere in the middle there has been an action that is actually a splitter between the states, okay, between the outcomes, and therefore you have to discover a state. So we concentrate only on those, and we basically, you know, identify the prefix, the action, and the suffixes, and this is the stuff that we put in the TTT algorithm. Okay, the 3 things, separating pattern, okay? How to get to the state that is the relevant state, how do you represent and deal with that state locally, and then what are the features, the distinguishing features. This has been applied by a gazillion of people, different from us, okay? For instance, Fides Arts and Frits van Drager in the Netherlands, in Nijmegen, they've used the LearnLib, okay, to learn a lot of very complex protocols. They are MR protocols, okay, for biometric passport, for TCP/IP or something like that. And so you see that by refining things, you can basically go from a picture that looks like this, where you have actually 262 concrete symbols, out of which 256 are basically different kinds of read file, because you're reading different elements, so to say, of a file or so. You can basically concentrate them in classes, so have alphabet refinements, and basically move to abstract symbols like the odd and the even, so the things that really matter, and you can have a much more readable representation. They are still big, and that shows scalability. Okay, TCP/IP protocol, same thing, right? You can have explicit data modeling. What if the data really means something and you don't want to just put it into categories, right? Well, you can, again, analyze counterexamples in order to find out new locations, new states, basically, new registers, so new entities that are storing data, and new transitions depending on the value of the data, right? So this still is has monotonicity, okay, it's monotonous, so it is, again, good from the point of view of the algorithm. And there are examples, actually, again, coming from papers that I can give you, so I don't go into details, but the point is actually that you try to, again, do the same game, right? How do I come to a location that is problematic in a certain context? In this case, it is the register where you, you register, let's say, in this case, it is a user access mechanism. So you're registering a user with a username 1 and with a password 2, okay? And then you can try to log in using exactly the same data, okay, 1 and 2, and it is fine. And if you actually try to log in without registering, you see that there is, in the second one, there is no registration. You try to log in without having registered, of course, it tells you no, okay? So this fact that you are registering is actually significant and basically allows you to split a state, right? So you had a hypothesis that told you, okay, you can basically do register and login, yes, but they have a sequencing, and therefore you can basically say, well, you first have to register, and then you can maybe log in, right? So that's one thing. The second is basically a splitter after you found out that the registering is relevant according to the data. If you try to log in exactly with that right combination of username and password, of course you access. If you're trying to use another username and password, sorry, you can't. So distinguishing values is important. So this is basically when you find, okay, that there was a new register, okay, needed, okay? And so here you basically say, well, yeah, but is X1 in the login equal to P1 and is X2 equal to P2? Yes or not? If yes, yeah, you can access. If not, you have a different behavior, okay? And then basically the login, so to say, that follows the registration is also making a difference. So you find out that there is a new transition, so to say, to a different state. Okay, so this is actually going from a one state to actually something that has a different number of states and very complicated labels, okay, that are expressing exactly the conditions under which the data is correct, okay, equality and inequality. Okay, and so you can basically see that instead of just having two states or something like that, you have more states because they are distinguished also according to the correct handling of data. And you see that these models look a lot like the models that people in system design like to have. And basically you could go from a model like this to an implementation to code in a very simple way, right? Because you have all the information that you need. Okay, so you can basically create a digital twin that is going to run in parallel with the system, right? Depending on what, you could also do the same learning, so to say, in the good old way with L-star, with symmetry reduction or non-symmetry reduction or something like that. You see that you would, in one case, you get this very natural, very logical register automata algorithm, register automaton, so to say, which is the model by means of using the register automata learning algorithms, 3 locations, 16 transitions, 400 tests, 3 equivalence queries, right? In the other case, you would have an incredibly difficult to understand model because it would have 73 states, almost 6,000 transitions. You would have had 415,000 tests and 72 equality equivalence queries, right? So you see, I mean, the huge improvement in efficiency that we have there, right? Now, if you have a stack of capacity 3, which is our example, okay, are you just interested to know whether a certain operation at that point is in the language, or whether also it leads to a right output, right? So you can, again, evolve from the register automaton that are just, like automata. It's basically a guarded transition. It just is a language recognizer, okay? Or whether you have really a Billy machine, okay? So a full a mini machine where you see the inputs and you see the outputs. Okay, so the RMMs, of course, have more information. And so if you just look at the data about, again, the stack with 1 position, 2 positions, 3 positions, 4 positions, etc. Okay, even if you go to 16, which is quite large, you still have a reasonable, let's say, performance. All the others are basically out of range, out of memory, out of everything, and it is quite fast, let's say, to achieve. And you can also work with procedural systems. I mean, what we saw at the very beginning with the digital twin, well, basically every node in this middle description of the application was a call, okay, to the procedure that is actually implementing the workflow for that action. So we have procedural systems. So there are extensions that also work with procedural systems. You see here a simple grammar, okay, with S and T as non-terminal. So those are the procedures. S is the main, and then you have just int is just you know, individual. It's just the very terminal, okay, operations, okay, and so these are basically you know, the automata that you get directly from the BNF for the terminals, non-terminal, etc. The straight lines, solid lines are actually working through the terminals, and the dotted lines are the calls, or the procedural calls, okay. So there is another representation that was proposed not so long ago, which is called visibly push down automata. I mean, so if you're working with procedures, you need a stack. And so the stack goes beyond the regular languages. You have a context-free behavior, and therefore you need push down automata. These are the visibly push down automata. Rajiv Allur presented them. And so they are basically context-free languages, so languages with procedures with matching call return, which is what you want to have, well-formed, let's say, call return. It's not that you're just, you know, having an infinite recursion that goes nowhere, right? And so you can work with this representation as well. And you can run examples. Okay, so there are papers from this. I'm just, you know, showing you a couple of patterns. So if you're just working on those kind of systems, so to say, with the regular approach, so regular languages, you basically work yourself to death, okay? If you're working in a procedural way, instead of working at the instance, you work at the class in a certain sense, or at the type of behavior. So you have a much more efficient behavior. And in some cases, the VPDA is really helpful. Okay, so you see in the LearnLib, we have versions of these algorithms that are working. You know, you can combine them. It is a multidimensional, let's say, space. You can choose your algorithm and choose the structure and choose the representation. And then you have your grid, so to say, of opportunities. So the TTT, okay, algorithm, if you're just applying it to a regular representation, is still, you know, doing a lot of work because you're doing a lot of, could I say, inessential work that you could save yourself. You see here that it is much better. It is, the symbol count is also the same. In some other cases, the VPDA is not really helpful, and so you're spending a lot of time and a lot of queries, okay, also with the better algorithms, with OP and TTT, right? Okay, same for the runtime and so on. L star, of course, is consistently bad. So, in conclusion, what is the impact of all of this? Well, we are able to learn digital twins, right? And I tried to make you make believable that we can do it with a fair degree of automation, with an unexpected degree of efficiency, with the precision that you want to have. And actually, I mean, and I didn't show that, also in an incremental way. So if you already have a system and you have to learn a variant of that system, you can basically start with that system. And as long as you don't have to retract parts of the model, but if you're just expanding, so to say, because we like monotonicity, you can basically start with a given system that somebody tells you, okay, so we know already this, you know, like for instance, a set of test cases from which you derive a first representation of an automaton, like the people that are doing passive learning typically do, okay? And then you can continue the exploration from there. We have shown that we are actually able to cover all these complexities that came up from here. So the fact that you are able to discover the structure, you are able to deal with procedures, you are able to deal with data, okay? And you can basically use as the language, the original language, the alphabet, let's say, the domain-specific language that is given by your system under consideration, under learning, okay? We had case studies in the early 2000s in different systems. So NASA Voyager, for instance, which is a simple but difficult to manage system, because now you cannot interact very much with that one. We wanted to know, in collaboration with Mike Kinchy, when he was still at NASA, so to say, whether it is done properly or not. So the way this has been designed, for instance, is by means of having a specific language for self-healing systems, which is actually what you see here on the right side, and then basically generating the models in the kind of DIME-like, like the robot, program description or behavior description in this case. You also see here that it is a procedural case. You also have data. The variables are actually these fluents, because the Voyager is able, for instance, to take pictures. It can do it with different colors in different cameras that are taking different colors. You have different antennas, so distinguishing the one from the other, of course, is relevant, okay? And the complex situation that we had was that we had this specialized description in this ASSL autonomous system description language, so to say, from which, just in order to validate what happens, LTS models had been extracted, okay? Out of this, they had developed Java code, which was, of course, independent of the models, because the models were just there for a description, okay? We had created, actually, JBC models, which is the models that I showed you on the left side, and we just added some annotation there for self-healing, because we wanted, there was a problem in one situation, so to say, and we wanted actually to detect and repair, so to say, that kind of situation. Out of these models, we generated with an automatic code generator the Java code, which included also the annotation and the facilities for the self-healing. And then the question was, okay, now we have two different kinds of models, two different versions of Java, okay? We can learn the models from the Java code. We just have this Java code, so to say, as a black box, and we just, interrogate that one. Or we can use those models, the design models, so to say, as the system, and basically see whether we end up with the same models. Okay, and also we could basically analyze the relationship between the behaviors between any actually of those alternative representation or alternative codes, right? So there was a specific commutation diagram, okay? So you start with a specification, you can basically transform it manually to this model, okay? Or you can generate the code and generate the Java, and then learn the model, so to say, from that one, and you want to see actually whether they are the same, okay? So going this way, or going that way, or going this way, you want to make sure that it is the behavior is the same. I talked already about the LearnLib. You can go online here and basically see that you are able to do a lot of work, so to say, with that. We had a lot of very successful industrial projects, the very early ones, Siemens, Telecom, etc. But other people also used the LearnLib, and they have published and got PhDs, etc., as much as you want. We have shown that it is possible to do model-based testing basically without having models a priori, because that's what we are doing actually by discovering the models. Lifelong learning is almost for free, because you can basically start with a model and extend it. You just need an initial test setup, alphabet construction, and then everything else can follow fully automatically. There is a very complex LearnLib, meanwhile, with a lot of features. So if you go online, you can basically, this is an even older, let's say, version of that. There is a lot of support in order to do this kind of analysis. Okay. And what we are now going towards is basically design for strategies. Okay, so design for analyzability, design for monitorability, design for verifiability, design for testability. Okay, so to basically, given the power of the machinery that we have, what kind of design level do's and don'ts, what kind of rules, so to say, can be extracted. And of course, out of this, there is the development since 2010 of an entire, let's say, series of workshops that are basically challenge-based workshops, like the Kaggle one. Okay, so these are the RARES challenge. Okay, for this kind of automata learning. And yeah, so the next issue, so to say, is going to be actually November 26th, I think, online. It should have been in October, but it has been delayed because of COVID. So if you're interested, you can just go to that URL and register and basically see, okay, what is going to happen, who is going to be able, who is able actually to learn most efficiently what kind of structures. Okay, so LTL, CTL, this kind of automata, that kind of automata, this kind of code, that kind of code, etc., etc. It's basically the digital twin automatic test generation thing. And that's what I wanted to tell you. Thank you very much.
Thank you, Tiziana, for a fascinating talk. I'll get that Kaggle link up there for you straight away. Does anyone have any questions? We can start in the chat, or you can unmute yourselves. I'm sure Tiziana will be delighted with your questions.
I have a question.
Okay.
Hi, Tiziana.
Hi. I know you.
Yeah.
Okay.
So Tiziana's my supervisor. So going back to the TTT algorithm, you had a load of, let's say, sub processes inside one state, if I read that correctly. So is there a possibility you can actually verify the sub processes all together, so have them fully model checked for all certain properties, and you can hold that all within one state of a model, if I'm right? I can't remember what slide number it was.
Yeah, no, okay. So yeah, the plain version of the TTT algorithm learns actually flat automata.
Yeah.
Okay. So if you connect it with a procedural approach, then you can basically separate the learning, and there is a complex management, so to say, of what is happening at what level. Okay.
Yeah.
So that's probably the most complex, let's say, mechanism that we have implemented right now. Okay. So there is a lot of thinking that goes into understanding, okay, not only, okay, what happens at the level of the entire system, which is always, of course, the reference model is, of course, the product automaton, of course, with all the state explosion problems, et cetera, and then how to reflect that onto the representation and work in terms of the representation, which is a procedural representation.
Okay. Yeah, because I was just thinking if you could actually, say, get the sub-process all verified, you could actually apply, say, formal methods, say, a pre and post condition into that state. You can actually have a pluggable, pluggable verified module.
Yeah.
Yeah.
The dream of
And
compositionality, exactly.
Yeah.
Okay,
I was thinking about that with the TTT.
Yeah. And the idea behind that is as much as possible. I mean, of course, I mean, if you have only one system, things can be complicated, but they are typically not complex. The complexity comes from interacting finite state machines. And typically they interact either with message passing, okay, that's one version, and the other is basically that they call each other. And so the idea is actually to try to have the possibility even to mix things, so where you have a model or a twin, so to say, for some elements. For instance, the ones that are devised and developed by a different group of people in your company, or customers, or vendors, or whatever it is, and you can have a different white box approach to what you are developing yourself, right? So that you can have this kind of mixed mode approaches.
Yep. Thank you.
Is there anyone else?
Okay, so I think it was a lot of information.
Hi, Tiziana.
Hi, Enrique.
Look, I don't resist to make a question. So look, I know that this is just only for students, but I like to match your presentation. And yeah, I will have surely the opportunity to go and review and learn something new from you. But look, one question that I would like to make is, because you were talking about this grammar and all of this stuff, and then I recall that grammatical evolution uses grammar. So could you please tell me, maybe, look, not only answering me that question, but perhaps extending a bit your explanation for the rest of the students, and trying to link your approach not only with grammatical evolution, but in general with evolutionary algorithms.
Good luck, because I'm not an expert in that field. So that's why, we should actually talk and work together. So my limited and probably incorrect understanding, let's say, of grammatical evolution is that you use the grammar as the guideline for the kind of substitutions that you can make in the system. So you're experimenting with this alternative, that alternative, et cetera, et cetera. So you're basically plugging in structures, right? We are not. We are just considering a black box. So it is just, we are discovering the behavior, the semantics, the semantics that is behind, let's say, the language defined by the grammar, and the language defined in this case, so to say, for this particular system, which is subset, so to say. The only thing that we are changing is the kind of grammar that we use. So is it just a regular language? Is it, do you have context free? Do you have calls? Do you have this and that, right? Do you see the inputs? Do you see the outputs, et cetera, et cetera? So it would be actually very interesting to see whether, we can correctly, reconstruct the systems, the behavior of the system, the semantic of the system that are generated by means of using a certain grammar of which you know the grammar. Because that's a sort of a gray box approach. You don't know exactly what system comes out, but you know the rules by which the systems, the family of all possible systems can be generated. In my case, we don't. I mean, it could be any kind of system, heterogeneous, implemented in all ways, hardware, software, whatever it is, and you just have an interface. So we are just, hitting onto the interface, right? So
wow.
That's interesting.
Yeah, we need to talk about that, because for me, it seems, I don't know if you agree, but for me, it seems to be a window of opportunity to make research in that field.
Yep.
Thank
That
you,
would be
Tiziana.
fantastic. Thanks to you. Yeah. Okay, so I would basically say just now, wearing again my hat of moderator, it was a lot of information. We are going to allow you, of course, and you're welcome to work with the tools, both the Alex and the LearnLib, and you're going to have 2 papers on this. And if you're interested in more, of course, you're very welcome. You can always contact me. I would just release you at this point into the short coffee break, and we resume actually in 10